So next we've got Joseph Marlow from the Scottish Association of Marine Science, and he's going to give us an update on another INSITE Phase 2 project, the NS3D project.
Hi. So I'm Joe Marlow, and I'm here to present on NS3D, and in particular some work we've been doing in just the last couple of months. And I'm here on behalf of the team, which does include John Halpin, who can't be here, but also Tom Wilding. So we are an INSITE Phase 2 project, and we're still going. The aim of the project is basically to significantly improve biomass estimates for marine growth on man-made structures in the North Sea. And our methods basically focus around computer vision, so we use a combination of photogrammetry and machine learning to do this. And our primary data source is intended to be industry ROV inspection footage, which, if you can harness it, is a potential gold mine. I've kind of highlighted these in different colors, basically to signify that one is going really well, we're happy with that, and the other is slightly problematic. But I'll go into a bit more detail. So, for those of you that are veterans of SIME, I apologize, you've seen this a lot, but I thought I'd go over our methods quite quickly. So there's kind of three parts. One is photogrammetry, which you can see on the left there. That is a model of Desmophyllum petusum, actually on my office floor. But it's a digital 3D model which was made from 2D images. So that's the idea. We can take this ROV footage and we can make 3D models from it. Now, if you're able to scale those models, you can measure things like length, surface area, and we're particularly interested in volume. And that's what this centre bit is all about here. For Desmophyllum petusum, and actually all kind of common North Sea marine growth species, we're able to basically plot their photogrammetry volume against their biomass. And we have nice regressions, nice relationships for each one of those taxa. So the third part of what we do is we'll get a 3D model that's come from an ROV bit of footage from, say, a wind turbine or a conductor on an oil platform, and obviously that's got a lot of species in it, and every single one of those species has a different density relationship. So we use machine learning to annotate that model by the different species. It's been trained to recognize different North Sea marine growth species. And it works like this. This is from a publication we had last year. This is actually done on a reef just off Sam's, but this is a 3D model, and we zoom in, we've got the model there. The machine learning nicely highlights the different marine growth taxa by colors, and then we're able to isolate the different taxa based on their color. And this graph kind of shows how well it's doing. We want all of these different taxa to be hovering around the 100% mark, because that means that our predictions are 100% in line with what the actual biomass is meant to be. Most are pretty good, anemones are a pain, but because they change size all the time, but their actual biomass doesn't. But for certain species, certainly the harder, more geometrically large ones, it does work very well. So, and we're able to do this with our ROV footage. We start with the footage, we make a 3D model, we then annotate it using machine learning, so in this case it's all red because it's all covered in Metridium, and then using some kind of coding wizardry, we're able to extract the biovolume and convert that to biomass. This was the dream, but if you were here last year, my colleague John Halpin went into a lot of detail about how inspection footage is problematic. Various elements of this. One is that actually we just kind of passive receivers of this footage. We don't really have any influence over the survey design. The ROV path is also, we have no control over that. So often if it's on an oil rig, the ROV will go kind of one single pass down a conductor or riser. It might spend a bit more time on a weld, but it certainly doesn't go all the way around. The video quality is shockingly bad, considering sometimes it was produced only in the past year or so, which has problems for our workflow. Not all footage is, but some of it, a lot of it is. Then we have problems of camera calibrations. This is how it's small problems and how the software calibrates the camera in the footage, basically build up over large models. So this here is actually, that is a model of a pipeline that runs over a few hundred meters. It's a flat bit of seabed, but as those errors build up. We start to get this burning effect, which is, it can be corrected, but it's not ideal. And I guess one of the biggest problems also is scaling. So we get this ROV footage and we can make a model out of it, but if we can't scale that model, we can't measure biovolume, we can't convert it to biomass. And we can use kind of in situ prompts. So if this is, say, this is actually a wind turbine jacket leg, if we know the diameter of that leg, we can scale the model. But if it's completely covered in marine growth, that creates problems. So what I'm going to talk about now is basically something that's happened literally in the past couple of months. It's taken some preparation, but our solution is not a new one. It's been discussed about plenty of times before, and that's actually to work a lot closer with industry to actually go about doing our own surveys. And what we've actually done is, I'm going to try and keep this anonymous and not say who it is or where it is, but we basically collaborated with an offshore operator, and we went on board one of their survey cruises just in May, and we use ROV downtime to direct our own ROV surveys. And a second part of that is that we are also given access to their online data archive, so we can look at past ROV footage in a kind of way that we've never been able to do before. We can literally type in the name of a particular part of the structure and find it and go look at previous footage. It was a 10-day cruise, and we didn't know actually how long we were going to be on the cruise for. So we decided to focus on Desmophyllum pertusum, used to be known as Lophelia. Plenty of work done on this in the kind of early 2000s, mid-2000s. Cold water coral, first found on these structures in the late 1990s. Early work's kind of done on depth distribution, growth rates, but we wanted to apply our new technology to try and estimate biomass, try and get an estimate of biomass for a total structure, start to get down to the nitty-gritty of how it changes across the structure, and actually maybe see if we can improve the growth rate estimates, or whether they're actually perfectly good as they are. So, survey design. We could design our own survey, kind of all things going well. So we focused on 5 different depths. All 4 faces of the jacket were kind of interested. Is the coral bigger or smaller, a bit of space and prevailing current, etc., and different aspects of the leg, vertical diagonal members, horizontal members. So there's about 80 different survey points, and at each point we were able to circumnavigate the component with the ROV doing a couple of passes. One of the big game changers is that this ROV came with a very special camera system here. This is a photogrammetrically designed camera system. It produces HD images, yay. It has 2 cameras, which means that just like our eyes, it's able to basically have depth perception, and it means that we can scale the models to a millimeter level precision. It also becomes pre-calibrated. And one of the wonderful things is it has a bit of software called VSLAM, which basically means that instead of us getting the footage and the next day, weeks later, we make the models and find this big hole in it, we actually get real time. So, can I play this? How do I play this? There we go. Left-hand image there is the actual footage coming off the ROV in real time, and the right-hand image is it producing a point cloud. So we can basically, it's got scale bars, which is very helpful, so we know how big the model's going to be, but it also means that we don't have any gaping holes in it. Really, really important for what we do. As I zoom on, this only happened in the past month, so we're just kind of showing early results, but it works quite well. So this is a portion of the leg, quite shallow, about 65 meters, about 4.5 meter length of it. And you can see the nice bits of Desmophyllum there. And what really helps is when we apply our machine learning. So they're all nicely highlighted. And what this helps us do is it really efficiently allows us to isolate the Desmophyllum from the rest of the structure, which should happen any moment now. We can then close that mesh, and because we've got this fancy camera system, we can instantly measure the biovolume. So in that 4.5 meter bit, we've got 2 meters cubed of Lophelia, and almost a ton of it in total. So we can start to replicate this across the entire structure. Other things we're looking at, this is kind of a series of cross-sections of the legs at 110 meters. It's not to scale in terms of the spacing, but we're starting to see some really interesting stuff here. Like what struck me immediately is that the Desmophyllum is actually kind of clustered around the inside of the legs, even though one would assume that actually you would see a lot more in the direction of the prevailing current when there's more food. We've yet to really kind of dig down into what this all means, but we're starting to see some of these patterns. All right, we're doing this. Finally, as I mentioned, we've been able to access some of the previous footage through their online database, and this is amazing. So for each of these models, we're able to search and find previous inspection footage of the model over different years. And because we've got this really great scaled model here, we're actually able to apply that scaling to previous models. And so we can track coral colonies through time. So this is, I think this is about 95 meters. This is a vertical diagonal member. This is 2025, so May, and the same one going back 15 years. It was really interesting. 15 years ago, there was very little desert island at all, and it has grown hugely in that time. We've seen recruitment of new colonies, but the various coloured circles track some of the colonies through time. And interesting, they all seem to be actually on the underside of these members. But it does allow us to actually do some kind of growth measurements, and for these colonies, we've kind of found about an average of a 50 millimeters diameter increase every year, which is actually in line with previous measurements. But because we're able to measure biovolume, we can also convert that to biomass. So just looking at this green colony here, that has increased in volume by about 0.1 of a meter cubed over 15 years, which is an increase in about 66 kilograms. But yeah, I guess in summary, I think we're all trying to get a hell of a lot out of industry footage because it's there and free, and it does work to a certain extent, but if you want to get the best information in, you've got to work a lot closer with industry and go about it in a kind of joined up effort. Thank you.